Start this section. This idea is the basic, beginning, fundamental knowledge on magnetism. Like the simplest stuff you can think of, we're starting with first. I'm going to assume no prior knowledge. But what do you know about magnets? Tell me. From middle school, from your experience using magnets in the past. Atticus, what do you know? Yeah, they have polar ends or polar opposites. Very good. As opposed to electrical charges, which are just positive or negative. Magnets have both ends of the system there. What else? Opposites attract. Therefore, what's the other term? Yeah, likes repel. Opposites attract and likes repel. This is stuff that you probably know already. I'm going to make that statement and we'll talk about why that is and stuff. But those are things that you should recognize, and they're very analogous to the electric force between two charged particles. An electron and a proton are opposites, and we said those attract, right? So a north and a south pole, those are opposites. They're also going to attract. In this section, we'll talk about magnetic field lines, what the field lines look like, just like we did with electric field lines. You guys did that electric field hockey thing where the puck was moving and stuff. And remember how you were able to see the field lines? And it really, I think at least, helps you to physically see a little bit better. Today, when I do a demo, I'm going to show you the field lines and what they look like using iron shavings. Okay, and you can actually do this demo on your own, but you'd have to have enough iron shavings and a strong enough magnet to do it. So let's start with this first. So first, we're looking at poles. We know that those are the ends, the north and the south ends of them. Let's draw a simple magnet to start. Okay, let's start with a simple magnet. So a magnet is traditionally drawn as like a bar magnet. Okay, something that is longer than it is wide, with a north and a south pole. Okay, with a north and a south pole. Now, as you guys said already, like poles repel, opposites attract from one another, similar to electric charges. Now, these are always going to come in pairs. That statement is just a fact. So, if I were to do this, and I were to cut the magnet in half, and then have two pieces below. Okay, I know this is south, I know this is north over here, and we're told that magnets cannot have simply one pole. It has to have both poles. So if I cut it in half, what do you think is going to happen as a result? Okay, so that's what's going to happen. You're going to have the south here on the right magnet on the left side and the north on the right side of the left magnet. So it's literally like taking an infinite amount of magnets next to each other. That's what a magnet actually is. And let me show you. I'll start with one thing first. I'll start with this guy first. So these are simple like disc magnets. Okay? And they're little like, what they look like, they're like coins. Okay, one of these was actually stuck on the board for most of the year, and I had trouble getting it off. I couldn't get off my nails. And today I was able to actually get off the mat. I forgot I had them. So the idea is that if you break this in half, it's still magnetic. So every one of these has a a north and a south pole on each side of the coin. It's like the heads or tails. So one part of it is north and one part of it is south. So if I bring this nearby, it automatically attracts the other. But if I take the two ends that are the same and try to put them together, it will not. It literally just flipped around. If I try to push them together, it won't work, and it'll flip around and invert itself. So if I were to take this entire magnet, which has, in this sense, a north end and a south, I don't know which is which, a north end and a south end, and just break it in half, well, if this was north, now this is now south. If this was south, this is now north. So when I bring them together, they naturally attract. Because when I broke it, I just created another north and south. I can break it over here, create another north and south. So every time you break a magnet in half, what you're doing is creating more magnets. Okay, you're never like stopping its magnetism by doing so. We're going to get into why that is with what's called magnetic domain theory. And we'll see a little bit more of that in the next section. But just know that every magnet itself is really like a bunch of magnets next to each other. So that was an example with these little coins. Well, this is the same thing now. Okay, believe it or not. So this is a magnet that has actually lost its magnetism over years. It's very heavy. Okay, it's made of mainly iron, but it's very heavy, but it lost its charge, or it lost its magnetism. These, like small bar magnets, though, they still work. So we know that those two attract right there, and if I try to push these together, they repel. Now, it's hard for you to see it, but if I were to take this one here, and this is something that I always say, like, I have a niece, and like when you have little kids, if you teach them about magnetism, it's going to blow their mind because it doesn't make sense, right? Think about it. Watch what I'm doing. If I bring this magnet here, look at the other magnet. It's literally running away. It's moving on its own completely and moving away from this. But if I bring this end instead near it, actually it's going to be if I bring this end even anywhere nearby, say like an inch away, it automatically pulls it toward it. Again, you've seen magnets before, but the concept is that it's a field force. Remember, a field force, not a contact force. A contact force means you have to have contact. Here, when it's even close by, I can feel the pull, and that's what a field force really is. So if you were to break one of these magnets in half now, as a result, instead of having north and south, you'd have north-south, north-south. 4 different parts. Again, if I cut this one in half, this is what I'm talking about right here. Okay, if I cut this in half, I then have a south, this end would be north, then I have another south here, and then this end would still be north. Okay, but this is really like what we're having here. Okay, this is the original, break it in half, well the magnetic field still exists, south, north, south, north. And like I was mentioning, this one, not magnetic. And we'll talk about how something can lose or gain its magnetic charge. Okay, the idea of a north and south pole on magnets really came from magnetic behavior on Earth. What do we know about Earth at the ends of the Earth? Not at the equator, but at the actual ends. What do we know exists there?
Isn't the north magnetic?
Yeah, we have a north pole and a south pole, right? So when you walk around with a compass, anyone that was in Boy Scouts or likes to go like hiking or Girl Scouts, I should say, any of the Scouts, if you use a compass, right, what does it tell you? What does it always point toward? What's the needle? What's the whole idea on a compass? Yeah, the shaded in part of the compass is always pointing north. And by north, I'm really referring to the North Pole. How is that possible when you think about it? Well, here's what's happening. Imagine this magnet right here is just a compass needle. Okay, it's on a freely spinning axis in the middle. Now, which way is north in the city? Point. Which way is north from here? That way, right? Okay, so yeah, kind of like at an angle, but maybe that way. That would be east, that would be west, that would be south. We should know our directional, right? When you go up in street numbers, you're going north. Does everybody know that? Right? Are we clear? Okay, just making sure. Some people don't know the directionals well. When you get off the subway and it says northwest corner, southwest corner, do you know how to use those?
I just know based on the...
Learn how to use it. It actually it's extremely useful. If you tell somebody, like, meet me on the southwest corner of the center, there's like no way you can go wrong. Or if you know you're getting off a train and when you're in a rush, like I'm a type of person who's always like running around, I like literally map out exactly where I'm getting off, just knowing. Because like, for example, if I'm getting off at 33rd and I want to go to 28th or 29th, right? And I get off at 33rd, I should get off at the south end of the train. If I know I'm going to go toward Brooklyn from there, I'm going to get off the southeast corner so that I optimize my time. I don't get off the wrong corner, I have to cross 2 intersections. I get off the correct corner every time so you're quicker. So you should know your directionals. I sit in anything, you should know your directions. So a compass, the way it's going to work is the north end of the magnet or the north end of the compass needle is going to point toward the North Pole on the Earth. But we just said a minute ago that likes repel. We just said likes repel. So how is it possible that the North Pole of the Earth can draw the North Pole of a magnet toward it? How is that physically possible? If likes repel, it doesn't make sense. You would assume that it should be this way, really. The north end should be pointing that way. South should be attracted to the North Pole on the Earth. So what's going on there?
It's a way larger. It's attracting all these other magnets toward it.
You're right in that statement, but that's not answering the question. The Earth is a much bigger magnet. In essence, the Earth is a giant magnet. Here's the Earth right here. It's a giant magnet, and one pole has different polarities. But my question is more of, it doesn't make sense that a needle with a north side of a magnet would point to a northern pole. There's a little, and it's ridiculous the answer you're gonna. So if you don't guess it, it's okay.
Maybe in every because it's north, right, and it's so big, right? Maybe because it's so big, there's space for the south, and there's some south particles in there. And
I like the theory, but that's not it. But I do like the theory, like thinking about like a lot of little magnets. Yeah. It's very ridiculous, by the way.
I think the North Pole magnet has south.
Yeah, exactly. When we name the poles, When we name the poles, they just name them the other way. So,
Yeah.
believe it or not, when you go to the North Pole, that's called magnetic south, technically speaking. Okay, it's absolutely ridiculous to think about it, but geographical north is the same thing as magnetic south. So when you go to the Arctic Circle up north, that's actually the south magnetic pole of the Earth. Again, it's very counterintuitive because you hear North Pole, you think it's the north end of a magnet. But for the Earth's magnetic field, the North Pole is actually the southern end of its magnetic pole. And now, it also turns out that it's not exactly aligned. It's right now, it changes a function of time. Right now, the polarity of the Earth is 11.5 degrees tilted from where it should be, or from where the actual axis of rotation would be on the Earth. Okay, so the rotational axis might be up and down. The actual magnetic field is tilted a little bit. And that has to do, we'll talk about that in this section also, that has to do with underneath the surface of the Earth, you have fluid, namely like some sort of magma, if you will, right? Some high temperature fluid that's flowing. That fluid has magnetic material in it. The actual convective flow, remember convection last chapter? The convective flow of that material underneath the Earth's surface is what causes the Earth's magnetic field. Now, because that flow is not constant, because the Earth rotates and over time things change, the actual angle of the poles, of the magnetic poles, has changed over time also. What's also interesting to recognize is that over a long period of time, the poles have actually reversed. So if you look at the Earth thousands and thousands of years ago, the North Pole might have been the magnetic North Pole at that time. Right now, though, again, the magnetic South Pole is up here at the North Pole. But for maybe 3,000-4,000 years from now, this might be completely switched. And again, that really, scientists actually to this day don't really understand it that well. But the idea is that it has to do with the actual convective flow of the actual material, the fluid in the Earth, and the rate at which it's rotating. Not revolving, but rotating.
Well, is it possible for the Earth to lose like the magnetism? Like you have that big magnet and it lost?
Yeah, that's a great question. Over time, the actual intensity or strength can change, but it's not going to lose a magnetic field because of its properties. But it can vary. And you'll actually see with magnets, like we were talking about earlier, how this magnet itself really lost its pole. There's very little attraction here between this, and this actually used to be a very strong magnet. And you can change that. You can actually make magnets stronger by inducing a magnetic field on the actual object. And I'll talk about that a little bit today, actually. All right, let's go to the next part. This is what we're going to talk about now, a permanent magnet. So a permanent magnet is simply something that is aligned so that it creates its own magnetic field. In chemistry, you learned about bonds, and some of the bonds were polar bonds, right? The bonds themselves are polar. You talk about each end having a different thing, like I think you even talked about like cathodes and anodes at some point being one positive, one negative. This is the same concept right now, and what I want you to think about for this is if a material, for example, like this rod here that's not very magnetic, if this material can become a magnet, all that it means is that its magnetic domains are not aligned. So right now, if this were the North Pole of the magnet and this were the South, all the material in the magnet would realign itself that the South Pole would face down. But right now, there's a lot of different like pieces. Imagine an infinite amount of little particles in here. They're not currently aligned properly. That's why it doesn't exhibit a good magnetic field. It's not a very strong magnet at all here. Whereas these other magnets we were using a minute ago are a lot stronger. They're able to actually attract to the actual board. So we can induce magnetism on something by using, and we're going to see this in the next chapter, a magnetic field that's come about from a wire. Okay, and usually a wire that carries a current also, not usually it does, also creates a magnetic field around it. So if you see, and I'm going to do this in a demo in a minute, if you see an object that's under the influence of a magnet for a long enough amount of time or magnetic field, it will get stronger. And we're going to talk now about two different types. You can have materials like humans, which are considered to be, in this case, really, by the way, everything gets affected by magnetic field. It's the level of effectiveness that they have. So humans are affected by magnets, but not to the level where we ourselves would become magnets. Whereas materials that are ferromagnetic, what does ferro refer to? Specifically, which metal? Iron, good. Things that have iron in them, ferromagnetic materials, can easily be made into permanent magnets. So the idea is that if you take a material that is very easily realigned, you call it a soft magnetic material. Okay, now we talk about in chemistry hardness levels, like diamond is very hard versus a material like sulfur. You ever seen a sulfur rock? It's yellow. You can scratch the surface of that with no problem. That would be like a soft material. In chemistry, we're talking about the quality of the surface. When I talk about hardness here, I'm talking about its magnetism. So if you say something is soft in magnetism, you would say that it can easily be made into a magnet. But over time, it will easily lose its magnetism. That's what soft magnetism means. Something that is hard in the magnetism level means that it takes a lot, whether it's time or a lot of current in that wire, it takes a lot of energy to make it a magnet. But it will retain that magnetic state for a longer period of time. So that's the difference between hard and soft magnetic. One, again, soft can be easily made into a magnet, but it won't remain a magnet for a long time. It will lose its magnetism easily. But things that are hard in magnetic cases, it takes a lot to make them a permanent magnet, but they will retain that magnetism much more readily than the others will.
Let's say it's a soft magnet, and it gains magnetism and then it loses it. Will it ever become a hard magnet, or will it just stay soft?
It's a function of the actual material. So if it's the same material, then that's just the material property. That would be soft.
Would that magnet be easy?
So this one here, this one? I don't know its properties. I honestly have never even worked. These were here before I even started teaching here, but they haven't worked since I came here. My guess is that this would be a hard magnetic material because these are, so when they sell these magnets for labs, usually they don't want them to lose their magnetism because you use them every year. So my guess is that this is what it would be. But unless I actually put this in a magnetic field over a long period of time and saw what it would be, you can't really tell just by looking at the material. It's very dense, it's heavy, I know that, but I can't really judge based on just looking at it. You know what I mean? But my inclination would be that it would be considered a hard magnetic material, so it retains its magnetism. But I'm pretty sure Mr. Donachek said these have been here since the 70s. These magnets were just in cabinets for a long time. Somebody bought them a long time ago, just they never threw them out. Because why did they not throw them out? Because of exactly this, right? It doesn't make sense to throw this out because you can make it back into a permanent magnet by inducing a field around it. Okay, and tomorrow we'll talk more about that with wires and circuits and how circuits are related to this also. All right, let's get into the last slide here. So the last slide, I want to jump into this demo first so you can see this. So the first thing that we're going to see here, the first thing we're going to see on this last slide, no, it's not. Hold on, air plays out. Give me a sec, guys. I'm just trying to get airplay back. Come on.
I think they,
yeah. Perfect. All right. So you see the scattered metal particles or the ferromagnetic particles. What we're going to do first is simply put one magnet in here to see the effect of this. These magnets are a little bit stronger than the other one I was using. Okay, so I need a pen. Okay. So everything's kind of scattered arbitrarily right now.
ooh.
See if you can see it starting to happen already. Okay, so look at the particles, look at them moving. Okay, watch the particles, they're going to slowly move. See how they're all gathering near the poles? See, these are all little iron shavings. They're moving in the fluid. And what's happening is it's developing a field that comes, which is the south end. I can't see. The red end?
Red.
Red?
I don't know, I can't see, but
Blue.
I'm assuming red.
So it's developing a field that exits here. It's going to happen for a little while. It kind of looks like hair almost, right? It's a little funky. So it's developing a field that's coming out of the north end of the magnet. The north end is the red end. Okay, it's coming out of here and going back around into here. Now from above, can you get from above now? Try to go from straight above. From above it might be even better. Try to get nice and close. Okay, so what we're having here, look carefully, we're seeing this curvature. The actual magnet on each end, each pole, this is exiting the field and then coming back around into here. Okay, this is kind of like the basic one first to start. Let me show you another one. All right, pause for a sec or just hold on. Let's see. So I have to shake this up again, unfortunately, or else it retains. So that, remember we talked about inducing magnetism? These little particles, in the other, when I was doing this earlier, they kind of got stuck in place. So I have to sit here and shake it up just to move them around a little bit so that they're, okay, now they're all settled back out again. What I'm going to do now is go ahead and put the magnets in with repulsive ends. What do you think is going to happen? You know what happens physically, right? Like if I try to push two north poles together, I can't do it. I can get them close, but it's still pushing apart every time. What do you think is going to happen with the iron shavings when I put these both in? What do you mean disperse? You're going to see them move away, but specifically from where? Not from both.
From the center.
Yeah, the center in between them, you're not going to see any particles because there's going to be a repulsive force. The force is pushing them apart. So if we do this one, let's take a look at this one.
Okay.
Start recording again.
Yep.
So they're pushing each other out already. So if I were to let go, watch this. If I let go of one of them, it shoots out because they're repulsive already. But if I sit here and do this for a little while, I can't get them any closer than this, unfortunately. Any closer doesn't work. But literally, look what happens. There's a repulsive force between these two particles in the middle, these two poles. So if I were to actually push them together, you see, look at everything bending. See, as I push them together, you literally see the particles bending away because they don't want to go near each other because the field that's established. So these are literally pushing apart in this case. Case 3 now. All right, this is case 3. So that was case 2. Case 3, what do you think I'm going to do now? Yeah, that was repulsive, so now I'll do attractive. Now what I have to do for this though, if I actually do this, watch. If I just connect them like that, what have I done? I just created a big magnet. So this is not going to be able to see anything if I do it like this. So I took a piece of wood, I just cut a little dowel down, and I'm putting this piece of wood in between the two. So you can actually see the field that's established between them. Okay, the last one, everything pushed away. There was nothing in this little space. But right now, even look at this, even this holds it. The magnetic force is strong enough to be transmitted through the wood and actually hold on. So I'm going to use this as like a spacer. Okay, so it's just a little spacer. I might even cut a new one next class and make it a little bit bigger, I think. All right, so let's let this establish for a little. Try to zoom in a little bit on it. Let it sit for a little second or two. It's more obvious from above. Can you get from above again?
Yeah.
Sorry. Okay, try holding it. Try to stop holding still. So what's happening here is this. Take a careful look. The actual magnetic field for each of these is established. So you kind of have this look where it comes out one end, back into the other, comes out one end, back into the other. But this is coming into this end. This is going out of this end. It creates an attractive force. So in the middle there, you're seeing that a lot of the iron shavings are actually connected between the two. It's so tough to see this on the board right now. It's so clear on the iPad too. You got any closer or not? Maybe that's a little bit better. Okay, so the field itself is coming out, around and back in, out, around and back in. But here, there's an attractive force physically between the two in the very middle. Thanks, Steve.
Right.
Awesome.
Is that it?
Yeah. And feel free to play with this if you want, or just don't break it. I'll leave it on the side for a couple days if you want to mess around with it, but it's really kind of cool. I mean, you'll see this stuff kind of do some weird things. You put the whole magnet in, you'll see everything start to retract. If you pull it away, it actually retains the magnetic pull for a little, and it looks like all little hairs like falling off there, right? But it's actually just iron shavings in this, whatever this resin is that's in here. Okay, but I'll leave it here for a couple days, but please don't break it or anything. Okay, please don't break anything from this. It'll get all over the place. That's why I say please be careful, don't break anything. All right, so let's quickly finish up this last slide. All right, how do I get rid of this now? How do I get back? I guess I can just hit delete, right?
Yeah.
Okay, there we go. Let me just move it out of the way for now. All right, so this is what we were looking at, right? This is right here we were just talking about a minute ago with that. So we see that the magnetic field line comes out of the North Pole into the South. Give me like maybe another 30 seconds to finish up last two things. So we talked about on the Earth with the poles being switched. We talked about how it's defined. Talked about why it happens on the Earth. The last thing, and this is like just a simple application, something I talked about in the other class, beings in general, do feel magnetism. You yourselves do. You just don't notice it. But there are certain beings that actually can detect magnetic poles, whether they're north or south. So certain bacteria actually have no sight, and they're able to navigate their way through things based on where the poles show them. So a bacteria will know that it's moving north or it's moving in a certain direction based on the pull it's feeling from the Earth's magnetic pull itself. If the value of the magnetic field on that planet is not great enough, then those bacteria will not be able to exist. If you look, If you look at Jupiter, or if you look at Saturn or Uranus, any of those planets, what do they have around them?
Rings.
They have those rings around them. Those are also a result of magnetic fields. If you've been to Alaska, the Northern Lights, Aurora Borealis, a result of magnetic fields. It's trapping particles in the atmosphere which cause those fluorescent-like, cloud-like, almost like gas-like look. Okay, it's all because of magnetism. This is just an introduction. All right, you have 2 homework problems. They are probably the easiest ones you'll ever do. It'll take you 5 minutes. Okay? Please.